Record. All right, Matt, please.
Okay. Hello, everybody. Welcome back to the Symmetry seminar. As usual, please feel free to ask questions. We'd like to encourage as much discussion as possible. Without further ado, it's a pleasure to have Dupay here to tell us about symmetries of 2D TQFTs and the equivariant Verlinde formula.
Thank you for the introduction. And before I start, I'd like to thank all the organizers for the invitation to speak. It's especially a pleasure to be giving this Easter special edition of the Symmetry seminar. And because this is a special edition, what I'm going for is the global minimum in terms of technical details. So I won't be talking about complicated quantum field theory with a lot of interesting dynamics. I'll be talking about some very simple TQFTs that has no dynamics and are in sufficiently low space-time dimensions. So these are 2D TQFTs. And in particular, I'll be talking about a class of nice 2D TQFTs that are semi-simple. Meaning that, first of all, they obey the original ATS-Siegel axioms. So what physicists could mean by TQFTs sometimes go slightly beyond the original axioms. So here, we'll make it a requirement that we are actually just talking about TQFTs in the original sense of the word. So the axiom tells us that if we are looking at a circle, then one can get a Hilbert space associated with this circle. I would denote that by V. And this is required to be finite dimensional. So a particular way of going slightly beyond what I'm going to talk about is to consider the case when V is infinite dimensional. It will not be a huge generalization, but that's something that we are going to exclude. And then if we are looking at the cylinder, it can be viewed as a cobordism between two circles. Then it has to be mapped to the identity map on V. Here, I guess a potential way of going non-semi-simple is by generalizing this so that this is actually some projection operator. But I'm actually not aware of any physically relevant 2D TQFT that has that kind of generalization. Furthermore, a slightly more interesting cobordism is given by the pair of pants. It's now a cobordism between two circles to a single circle. And in the TQFT language, this is assigned to a linear map between two copies of V to a single copy of V. What this does is that V will now be equipped with an algebra structure. So there is a product structure on V. And this algebra is actually commutative because here the order does not really matter. So it's commutative. Another interesting cobordism is a cobordism given by a cylinder viewed as a cobordism between two circles to the empty manifold. Then this gives a symmetric pairing on V. So here I'm working over the complex numbers. So for the empty manifold, the TQFT would assign to it the underlying field C. And then this is non-degenerate by linear symmetric pairing. And I will denote it by this parenthesis. And this data fit nicely together. And they form algebra known as commutative Frobenius algebra. And in fact, TQFTs are classified by commutative Frobenius algebras, in the sense that in the opposite direction, if I'm given a commutative Frobenius algebra, I can construct a 2D TQFT. And then here we'll require that commutative Frobenius algebra is also semi-simple. So one feature of semi-simple commutative Frobenius algebra is that it can actually be diagonalized. If we are working over complex numbers, so V will be given by sum of one-dimensional Frobenius algebras, and each is specified by a number. So I will use the letter B to denote the label set. And this number has a property that none of them are 0. So for each C that is one-dimensional commutative Frobenius algebra, and the generators of these one-dimensional guys will not talk to each other. So if one computes the inner product between the i's and the j's subalgebra, this will be a delta ij. And if one is taking products between E and EJ, again, they will not talk to each other, so this will be a delta ij. And then this lambda will come in times EI. So an example of a possibly non-semi-simple commutative Frobenius algebra is given by the cohomology of a manifold. You can try to, for example, take the cohomology of CP1 and then try to diagonalize it, and then you realize that that cannot be achieved. So it seems that I'm restricting myself to a special case where I'm only allowed to talk about very nice 2D TQFTs. But actually, there is an abundant supply of such 2D TQFTs. So there are many examples. At least as many as rational conformal field theory that can exist. Because if I take a rational conformal field theory, then there is going to be a fusion algebra that's actually can be made into a commutative Frobenius algebra. So here, this lambda will sometimes refer to them as fusion eigenvalues. And for this product structure, we'll sometimes just refer them as fusion rules. So the name obviously comes from rational conformal field theories. So the algebraic structure of rational conformal field theory is captured by mathematical objects known as modular tensor category, MTC. And if I'm given MTC, then that leads to a commutative Frobenius algebra. And the algebra is just part of the modular tensor category. Alternatively, you can find Frobenius algebra by looking at three-dimensional TQFTs. So maybe nice TQFTs to avoid something that is not semi-simple. So for nice 3D TQFT, and you have Wilson lines, and they will have a fusion rule. They'll have an algebra, and that also turns out to be commutative Frobenius algebra. So you can find such 2D TQFTs in a lot of places. So one famous example is given by the algebra of Wilson lines in transamination theory. Then the corresponding rational conformal field theory is the West-Domino-Witten model, WZW model. There's also a more tensor category associated with it. It's some simplification of a small quantum group, so I will not write it there. But all of these three will depend on choice of group G. From the point of view of transamination theory, that's the gauge group, and then a level K. When G is a simple Lie group, K is simply an integer. And then the commutative Frobenius algebra that corresponds to this is known as the Verlinde algebra. So it controlled the fusion rule of the Cairo WZW model and also the algebra of transamination theory of Wilson lines in transamination theory. So to give a very simple example, consider G being SU2. Now the level is literally just integer. I will assume that this is positive. Then the dimension of the underlying vector space V is going to be K+1 dimensional. And there is a nice basis given by W0 through WK. And they're labeled by weights, lambda, or equivalently irreducible representations of SU2. So for example, in a sense, this W0 corresponds to the trivial representation of SU2, and W1 would correspond to the two-dimensional representation of SU2, W2 will correspond to the three-dimensional adjoint representation of SU2. And then
what
there
happens
is
if you had instead of SU2 or something like SL2C? How does this the topological side generalize if you had infinite line?
So right, so if I replace the group to some to a non-compact group, what happens is that I can no longer call the TQFT a nice TQFT, so it will not directly give you a nice finite dimensional Frobenius algebra. But what happens is that there are often ways of regularizing it. So somehow find a parameter that interpolate between the compact case and then the fully fledged non-compact case. So that's will actually be the context of Equivariant Verlinde formula. So in that case, instead of having something very crazy, one actually just have a nice family of 2D TQFTs.
And could you say what's the relation between the 3D TQFT that you're talking about here and the 2D TQFT that you would like to construct?
Yeah, right.
You put it on a scale or?
Yeah, so they are just related by dimensional reduction. So from 3D TQFT to get the 2D TQFT, I just compactify on S1. And I get the 2D TQFT. So if I do this to transamination theory, I'm getting a 2D TQFT that is, well, cannot be WZW model. WZW model is a theory with dynamic degree of freedom. So instead, I will get the gauge gauge WZW model. That's the 2D TQFT that I get by compactifying transamination theory on circle. So any other questions?
I'm confused by the fact that you assume that the spectral space is finite dimensional. Given the classification, I believe you're talking about bordisms with orientations. And in that case, it's a theorem that the vector space has to be finite dimensional. The bordisms you've already drawn on the slide, the co-evaluation, the evaluation.
Yeah, yeah.
Also-
So there are some other axioms, and that if you assume some other axiom, then this being finite dimensional would be something that is necessary. For example, if you want the partition function on T2 to well define, so this count the dimension of V. So then it will be automatically finite dimensional. But physicists actually sometimes talk about TQFTs that have infinite dimensional Hilbert space. They just have to give up some of the partition functions. So one famous example is 2D Young muons at zero coupling. So that theory does not have a well-defined partition function S2, does not have a well-defined partition function T2, but actually for higher genus partition function, it's well-defined. And it's very interesting physically. So here, one can say that, well, they just fail some of the axiom of the standard TQFT. So, but well, one can just relax the axiom slightly so that the 2D Young muon theory can still be viewed as a 2D TQFT.
Which axiom do they fail?
So, for example, this guy will not be well defined, and also the co-unit will have some problem.
Yeah, but
Sorry,
you don't
the
need
unit will have some problem.
You don't need the unit or the co-unit to get that the vector space is finite dimensional. And it's not acceptable to just have the theory not well defined on the torus, because I'll cut the torus open and turn it into an evaluation and co-evaluation map. So your theory is not functorial. Yeah,
yeah. So there are some a problem with some other axioms. So here I'm just giving an example that you can see that torus partition function is not well defined. So therefore, some axiom has to be violated.
And if I can make another comment, I mean, you commutative.
So if you look at, for example, cohomology of CP1, that's actually commutative. So in general, yes, if you are want to include example like A model or B model, where naturally the Hilbert space is graded, one need to make this axiom modify slightly so that it's graded commutative.
Okay, thanks.
So in the Verlinde algebra, there are going to be some very nice and very familiar products. For example, if I take 2 times 2, provided that k is not too small, this is giving familiar decomposition of angular momentum that we learn in quantum mechanics classes. 2 times 2 equals 1 plus 3. Or written in terms of these generators, W1 times W1 equals to W0 plus W2. So to be maybe more precise, one can write down the pairing between 2 arbitrary basis vectors. So this is delta. Oh, let me maybe use lambda I, lambda 1, lambda 2. And then if I multiply W lambda 1 and W lambda 2, so in general, I get a sum over the set of allowed W lambda 3s. And this F is often referred to as fusion coefficient. So in this case, they take a very simple form. So this can only be either 1 or 0. This is a special feature of the SU2 theory. And it is a 1 if the sum of lambdas, lambda 1 plus lambda 2 plus lambda 3, is even. And further, lambda 1, lambda 2, lambda 3 satisfy some relation so that this triangle. So instead of saying very precisely what's the condition, let me just say that this triangle, first of all, they form a triangle, namely one of the lambda should not be large enough. And further, this triangle fit in the Lie group SU2. There's a better way of saying this by defining some quantity, and that quantity has to be positive or non-negative, but at a technical detail, and it will be 0 otherwise. So this condition is something that is natural if you really think about fusion of line operators in transaction theory. So there, Wilson lines are also vortex lines, and they carry particular monodromy. And you want to make sure that if you fuse two different things, this monodromy is consistent. So in particular, if you are considering this special guy, well, it has lambda equal to k, so that's a very long edge, and then you multiply that to itself, and there's only one thing that you can get. So this would look quite different from the usual tensor products of representation of SU2. Instead of having a lot of things up to W2k, you only have a single guy. And furthermore, if you take the products of WK and W lambda, then you will still only have a single guy. That's WK minus lambda. So here, you already see a clue of some symmetry. First of all, there seems to be a selection rule. You want this sum to be even. So selection rules are often related to symmetry. And also, this omega k seems to be special. It acts on different things, producing something else. That looks like symmetry. So this 2D TQF actually have some very large, it has a very large amount of symmetries. So for example, you can have—
Hey, can I ask a question?
Yes.
Is there any good reason why the F coefficient of
Sorry, can you say again?
is there any good reason why the F coefficients are Z2 value?
Oh, are equal value?
Are Z2 value?
Sorry, Z2 valued?
Yeah.
So it's a special thing that happened for SU2. So if you look at SU3, SU4, or even SO3, well, in the case of SO3, there is some different way of defining the fusion coefficient. But if you look at general Lie groups, it will not be the case that it's like Z2 value. So
is there some specific general pattern that you might expect? So,
I'm not sure whether there are general patterns. Of course, you can look at bounds on the fusion coefficient, or just look at the bounds on what kind of multiplicity that can arise by taking tensor product. So for a given group, and if you take products of irreducible representation, there are often some upper bounds, but I'm not sure whether there is a good like unifying theory for it.
sorry, just out of curiosity, what is it for SO3?
For SO3, for SO3, some of the fusion coefficient can be actually 2. So we will talk about the SO3 case later, but actually that would be in a different basis. So anyway, so hope that answered the question. So
Thank you.
so this TQFT actually has a lot of symmetry. In particular, it has non-invertible symmetry. Well, simply because in transaminase theory, all the Wilson lines are topological, and they generate large non-invertible symmetry. And under the reduction, you also have Verlinde lines that generate a lot of symmetry. But today we'll actually be just looking at invertible symmetries. So part of the reason is that later I'm going to deform it related to Sakura's question about what happened to non-compact group. And the way that I deform it will be by introducing some matter that will actually break the non-invertible symmetry, but will preserve the invertible symmetries. In the case that we, in this SU2 transaminase theory or SU2 Verlinde algebra, there's going to be two Z2 symmetries. So one is a usual Z2 symmetry or Z2 zero form symmetry. Another is a generalized symmetry, that's a one form symmetry. And they act on the Hilbert space. So generator of one form symmetry, that's a topological line or topological domain wall in general. So therefore I can insert it like this along a cylinder. Then I'm no longer having the identity map between V to itself. I'm now having some non-trivial map. And because if I have two copies of this, they cancel since it's Z2 value. This leads to a Z2 group action on V. For one form symmetry, that's generated by a codimension 2 defects. It's going to be again a topological defect. And if I insert this, then I again get an action on V. So they both can act on the Hilbert space associated with the circle. And the action in the basis that we gave is the following. If I now take omega lambda, sorry, W lambda, this is mapped to -1 to lambda, W lambda. So the zero form symmetry in this basis just acts by a phase. And the one form symmetry will map W lambda to WK minus lambda. So the first one is related to the selection rule in the sense that it explains the selection rule. So why is that the case? If I'm now looking at cobordism like this, and then insert a Z2 line, because this is topological, I can move it very close to this part, or move it very close to these two incoming boundaries. Therefore, for any fusion, for the fusion coefficient to be non-zero, we better have the action on lambda 1 and lambda 2 be the same on the action on lambda 3. So that's where this relation comes from. So in if you are dealing with just well, representation of SU2, one can say that this is just this action of the center on the corresponding representations. The action of the center has to be compatible. How about the second guy? So the second guy is going to be actually generated by WK. So this is going to be in the sense that the action is just a fusion with WK. So one thing that one would immediately notice is that actually the two actions in general may not commute. So they only commute when K is even, and they will have a mixed anomaly, namely they will not commute when K is odd. So that's when the generator itself for the one form symmetry is actually charged under the zero form symmetry. So what's the general story? So here in this spaces, the action is something very nice. But maybe you can imagine that, well, the action maybe can be quite general. Like in quantum field theory, we see all kind of very general action of symmetry. So what's the story? It turns out that the way to really constrain how symmetry can act on 2D TQFT is by looking at the basis where the fusion will become diagonal. So in a diagonal basis, then zero form symmetry has to act by permutation. And one form symmetry has to act by a phase. That's actually the opposite of the action on the on this preferred basis that corresponds to a nice representation or nice Wilson lines. So the basis that is diagonal is going to be, in a sense, Fourier transform of the previous basis. So that's the, well, basically saying that the S transformation, the S matrix diagonalize the fusion rule. And the S matrix, in this case, look like a discrete Fourier transform. So these two statements looks pretty simple, but they have some interesting consequences. For example, one consequence of the action of zero form symmetry is that if I look at action of connected Lie group, it has to act trivially. Because I can no longer have a non-trivial homomorphism to the symmetry group. Acts by permutation action of a symmetry group, a permutation group. And furthermore, it can only permute basis vectors that have the same fusion coefficients. So if the fusion coefficients are all different, there can be no zero form symmetries. So how to see something like this? So I will spare you from the complete proof, but just give some illustration of the general, the intuition behind this. So if you have two one-dimensional subalgebra that has the same fusion eigenvalue, so this is one of I, then you might imagine that you can actually rotate them into each other. So they are normalized so that the inner product equal to 1, and then the product between E1 and E2 will equal to 0. You may imagine that I can just send E1 by A times E1 plus B times E2. So to preserve the inner product, maybe I want some orthogonal action. So A squared plus B squared equals to 1. But then the first equation now looks like the following. It looks like A squared E1 squared plus B squared E2 squared equals to lambda times A E1 plus lambda B E2. And using the filtering rule, this equals to lambda times A squared E1, and this equal to lambda times B squared E2. And lambda is non-zero, so we cancel it. And for this equation to make sense, A squared has to equal to A, and B squared has to equal to B. So A and B can only be 0 or 1, and there can only be a single 1. So either A equals 1 or B equals 1. So it has to be a permutation. This argument can be made, can be generalized, and in general, you can prove that zero-form symmetry always acts by permutation in this diagonal basis. So you can now just infinitesimally rotate two eigenvectors, even though they have the same filtering eigenvalue. For one-form symmetry, the story is similar. So for one-form symmetry, if you look at this, then because of the topological property of the symmetry generator, it has to equal to this one. But since the filtering rule is diagonalized, this is proportional to EJ, and this is proportional to EI. So if EJ and EI are different, it has to be the case that you have 0 equals 0. Otherwise, there's no way for this to be equal. So you cannot rotate EJ into EI or EI into EJ. And it has to rotate EI into itself. So G times EI, that has to be some phase, some one-dimensional representation of your symmetry group. And if you assume that your symmetry group is compact, then it can only act by a phase. So in general, this is a complex number. But well, we'll be dealing with a compact symmetry group. So it will be a phase. And if you further assume that it's discrete, then it's going to be a root of unity. So that's how 0 and 1 form symmetry acts on semisimple 2D TQFTs. So equipped with this knowledge, then we can consider gauging of these symmetries.
Can I ask a question?
Yeah, please.
Why do we call this 0 form or 1 form symmetry?
So this is so because they are generated by topological operators in different dimensions. So this 0 form symmetry will be the usual symmetry that's generated by topological domain walls. So if I have something that is charged, then I surround it by this wall. I pick up a phase, well, pick up a factor telling me what's the charge of it. And if I have some other something that is charged under 1 form symmetry, so in general, it will be charged objects are going to be some lines. Then I have to use codimension 2 objects to detect this charge.
So maybe a related question. If you think of this coming from 3 dimensions on a circle, do both of these arise from the same 1 form symmetry in 3 dimensions?
Yeah, exactly. So
whether the defects wrap the circle or not, right?
yeah, that's exactly right. Yeah, so three-dimensional SU2 transamination theory will have one form symmetry, and if you reduce that on a circle, you have either zero form symmetry or one form. Well, you have both, and then the one form symmetry in 3D can be anomalous, and that's exactly the anomaly that we were talking about. But now it becomes a mixed anomaly between the zero form symmetry and one form symmetry.
Here, all those E sub 1, E sub 2, I actually think of them as the basis of local operators, right? This is local operators.
Yeah. So
and what about the W
operators.
above? What is W?
They're also local operators, but they're just in a different basis.
Okay.
So, but they are actually related. If you want to leave to the 3D perspective, they are exactly related by the edge transformation. So if you have lines, there are different ways of getting elements in the Hilbert space. So, and you can, well, because the Hilbert space involves a circle, and then you have the other circle. The two ways are related by the edge transformation. So that's an interesting story in its own. But
the generator of the one form symmetry are part of the actually just the local operator you're considering, right?
Yeah. In this case, it will join. It will be a local operator.
Okay. Thanks.
No problem. So let me quickly mention what happened with gauging. So if I take a theory with symmetry, zero form symmetry G for simplicity, I will assume that this is going to be abelian. So it's something like, well, product of cyclic group, maybe just a single copy of Zn. So then in the original theory, if I look at particular like idempotent and the fusion or, well, eigenvector of the fusion rule, then G would act on this, so there will be an orbit. After gauging, I will get either one or more vectors, and they are labeled by L, which run from 1 to the order of the stabilizer of the G action on E. Then the fusion rule, so the fusion eigenvalue will be given by lambda I times the order of the stabilizer divided by square root of the order of G. So that's how to get the TQFT after gauging an abelian zero form symmetry. So if you look at the partition function, so two TQFTs or semi-simple TQFTs, their partition function are particularly simple. So it will be a sum over this label set B, and then lambda I to the power 2G minus 2. So that's the original guy. And if you gauge it, then now you are only going over orbits of G. And then you have this vector because for any orbit, you can get many vectors. And then, well, let me just write lambda I tilde to 2G minus 2. So the actual ones that one gets are can be referred to as states in the twisted sector. So they are associated with having a non-trivial holonomy of G on the S1. So this is the gauging of zero-form symmetry. How about one-form symmetry? For one-form symmetry, let me deal that by F. One-form symmetry are abelian. So let's again assume that it's something like a Zn. Then you will have only those EI that are fixed by the entire F. So these are the only things that will survive. So if I is in the fixed point of F in B, and then the fusion eigenvalues will be the original ones over square root of the order of F. So that's how you would gauge a one-form symmetry. So a few remarks. So if one gauge a symmetry, the dual symmetry would arise. So if one G is abelian, if you gauge G, then what happens is that there is going to be a dual symmetry. That's a punctual eigendual of G acting on the resulting field. And then you can use this description to check that if I gauge it again, I can get back the original field.
What is the dual symmetry for the one-form symmetry?
Yeah, that's going to be the next remark. So the first remark is just about the dual symmetry of the zero-form symmetry. So here you see that this factor is exactly necessary to get back to the original theory. So the second remark is related to the question. So notice that if I'm gauging zero-form symmetry, sometimes I have a bigger Hilbert space, sometimes I get less. But it seems that if I'm gauging one-form symmetry, I'll always lose something. I only look at something that is completely fixed. Sorry. But actually, you still get dual symmetry. But that's not symmetry in the usual sense. It can be referred to as a minus one form symmetry. But that's just a fancy way of saying that now there is going to be a discrete parameter in your theory labeled by an element in dual of F. This can be, well, in higher dimension, we will call this discrete theta angle. In 2D, it's often referred to as discrete torsion. So I'm actually not losing anything. So for any, for states that are completely invariant, they're in the theta equals 0 sector. But for some states that transform non-trivially under the action of F, well, there is a particular theta that where that give you a sector where that state lives in. So I'm actually not losing anything. And if I gauge the minus one form symmetry, meaning I put together all those different theta sectors, I should get back the original thing because I'm not losing anything. So let me, well, another remark, I'm not going to write it, is that this story can also be generalized to the case where we consider extended to the TQFTs. So namely, we are now allowed to consider boundary conditions. So then there are different ways of describing that. One way is by using Calabi-Yau categories. And there you can generalize the statement and the procedure of gauging. So, but instead of talking about Calabi-Yau categories, I will be returning back to the example of SU2 level K, Verlinde algebra. So I will draw the fusion eigenvalues actually on a circle, because, well, the original basis, these nice bases are labeled by representations. If I perform an S transformation, then it's going to be labeled by conjugacy classes in SU2. So they are labeled by particular points on the carton of SU2, which is a circle, but using a Wild symmetry, it's a half circle. Then I will use, well, the vertical axis to denote the fusion eigenvalues. So in general, I have some discrete set of points that live on this circle. The picture for even odd k are going to look somewhat different. So if I draw the case 1, case even, then there's going to be a special thing over here. If case odd, then there will not be a thing at the symmetric point. The Z2 zero form symmetry will act by flipping along the vertical axis. And the Z2 one form symmetry, oh, sorry, I'm saying this in the opposite way. Zero forms, what am I doing? This is zero form symmetry, this is one form symmetry. Yeah, Z2 one form symmetry would act on this with some phases will be plus minus, dot dot dot. So then you can see that if I gauge the zero form symmetry, what happens is that I'm identifying the orbit of this Z2. And then this guy will become two different objects, one in the n-2 sector, one in the 2 sector. If I gauge the Z2 one form symmetry, I will kill everything where this Z2 acts non-trivially. So if I start with the SU2 theory, then I can gauge either the Z2 zero form symmetry or the Z2 one form symmetry. Then I'll get two different theories. Let me just use this symbol to denote these two different theories. And then I can gauge the other symmetry, provided that there is no mixed anomaly. Then that theory is perhaps should be called the PSL or SO3. Let me just use notation SO3 theory. And these two theories can be obtained from 3D by working with 3D, either SU2 theory or SO3 theory. Namely, one can gauge the one form symmetry in 3D, and that amount to gauging both the zero form and one form symmetry in 2D. But for these theories, you cannot realize them just by dealing with the 3D theory. And the existence of these all four theories has some interesting consequences. So in the previous study of Verlinde formula, there's an observation that there's a particular well, space of discrete, non-abelian theta functions that the dimension looks like a partition function of TQFT, but that actually correspond to one of these theories. So if you just use the 3D theory, it's hard to explain the nice form of that formula. But if you now understand that actually in 2D there are four different theories, then that explains that interesting observation. Another interesting observation is that when mathematicians study Verlinde formula associated with S23, in the formula, one need an additional state if I want to do cutting and gluing. And that's exactly this additional guy for the twisted sector. So I will end with some comments about deformations. So that's related to the question about non-compact groups. So instead of working with 3D transamination theory, one consider 3D n equals 2 transaminance matter theory. So this will be super transaminance matter theory. And one can consider a particular kind of matter that can preserve all these symmetries. That's the adjoint matter. So physically, this is going to be a 3D n equals to chiral multiplet. And then one consider this on S1 times sigma. There's a way of performing a partial topological twist on sigma so that actually one can still get a 2D topological theory. This adjoint matter, again, chiral symmetry. But because we know that U1 symmetry, if we reduce to a zero form symmetry, it has to act trivially. So the only way that this enter in the 2D setup is in a form of a -1 form symmetry. So that's basically the holonomy of this U1 S1. So in 2D, instead of getting a single theory, one get a U1 family or C star family of theories labeled by this T parameter. So instead of having the usual fusion rule, 2 times 2 equals to 1 plus 3, now instead one have 2 times 2 equals to L, some factor, times 1 plus some factors times 3 and 5, that's 1/4. Notice that 2 on the right-hand side is still excluded. So that's telling me that the symmetry is still there. The selection will still apply. But now you get actually more things. In fact, everything that is allowed by symmetry is going to be there. So what is this new algebra? Why is it something that one would be interested in? Well, that algebra actually knows about some interesting geometric moduli space. So this algebra gives or controls the geometric quantization of the Hitchin moduli space or moduli space of Higgs bundles. And the particular function of the 2D TQFT are in a sense dimensions regularized of complex transamination theory. Of course, understanding complex transamination theory is something that is very interesting in its own right. And this formula also have some interesting mathematical applications. For example, we can use this to probe the geometry of the Hitchin moduli space. So it can be written as certain integral over this moduli space that denoted by MH. And the U1 would act on this moduli space. This is a famous Hitchin action. And then one can apply equivariant localization formula to decompose it into a sum over fixed point of the U1. So and then this can be used to probe the geometry of the moduli space of Higgs bundles. So I'm running out of time, but let me maybe just have one quick remark. So before, what I mentioned is that in this diagram of 4 theories, two of them can be lifted to 3 dimensions, and they are two more interesting ones. But actually, if you consider this deformation, everything can be lifted to 6 dimensions. So there is the perspective from a string. So if you consider either M5 rings or more generally 6 to 2,0 theory, a length space times sigma times S1, then that partition function, one can preserve supersymmetry, and that partition function is actually a 2D TQFT on sigma. That's exactly what we described. And then if one first compactify on this L, then one gets some this 3D n equals 2 Chern-Simon theory, Chern-Simon symmetry theory. But when it's not necessary to first just compactify on this length space. So there are more general partition functions of this system. And there are different choices that lead to different partition functions and different 2D TQFT on sigma. So to get interesting 2D TQFT on sigma, one would try to find something known as polarization LK, 1 times S1. So due to a lack of time, I will not carefully explain what this is. But different versions of the 3D theory come from polarizations on M3, which is now LK, 1. So for this guy, they only know about some of the theory, but there is the embedding of polarization on M3 into polarization on this product, and everything actually can be found here. So some of the 2D TQFTs that has been constructed, it cannot be lifted to 3 dimensions, but they can always be lifted to 6 dimensions. So sorry for running a bit over time, but let me stop here. Thank you all.
Thank you very much. Okay, questions? Feel free to shout out if you have any. Otherwise,
so if you take a different 3 manifold instead of the length space, but something more complicated, then do you always get on sigma something that falls under this class of TQFTs that you discussed, or what's the condition on M3 to actually get something that is of this
right
type?
So in general, if one just take an arbitrary 3 manifold, what one expect is that one get a TQFT that is not good, in the sense that it may not be a semi-simple TQFT that I'm describing. So here in this system, it's crucial that hidden somewhere there is this U1T symmetry that I have used, and the analog of this U1T would be there if this M3 is ciphered. Basically, for cipher manifold, there is a particular singular limit of the shape of the geometry where you see some geometric U1 action, and that's the something that one can use to make this 2D theory well defined. So for cipher manifold, one certainly expect that something is there. But then for general 3 manifold, you still expect that, well, there's something. It might not be semi-simple, might not be very nice, but it could be something like the 2D Yang-Mills theory, which is you define on something that's not satisfy all the TS-single axiom, but still interesting. So
are cipher the most general ones to give you to these finite dimensional guys, or could also graph manifolds be?
Yeah, I would imagine that it can go well beyond a cipher. So semi-manifold constructed by a plumbing graph should lead to also nice 2D TQFTs, and maybe one can even go beyond that. So it's not clear where's the limit.
So maybe I could follow up on that. If I put aside the connection to 3 manifolds and just ask about 3D n=2 Chern-Simons matter theories, is the condition that there's kind of a finite number of solutions to the beta equations? Is that basically what you need to happen?
Yeah, so if I'm looking at Chern-Simons matter theory, I would always have finite many solutions to the beta and delta equation. So this is basically the solution to the beta and delta equation. So from the 3D point of view, that's indeed always the case. But if I just take a random 3 manifolds, it's not expected. I'm always getting a nice Chern-Simons plus matter theory. Even for cipher manifold, this is not clear. So but indeed, for Chern-Simons matter theory, with all kind of matter, one can turn on different deformation parameters. And the story there is also interesting.
And to what extent does this, in terms of this parameter t, to what extent does it kind of take you a bit outside of the axioms that you would normally consider? I mean, how should I think of expressions like on the slide here, where there's a denominator? Is it more like there's a symmetry and you grade the Hilbert space by the symmetry? So the Hilbert space is infinite dimensional, but provided the graded pieces are finite dimensional.
So that's a perspective from the 3D theory. So for the 3D theory, indeed, the Hilbert space will be infinite dimensional, but then there's going to be a U1 action, so it's finite dimensional. But from the 2D TQFT perspective, the dimensional Hilbert space is still, in this case, k+1. So that's not deformed. You still have the same set of vectors, but their fusion products become deformed. But it is fine to have this. Fusion coefficients are not necessarily integers. So in general, for general 2D TQFT, they are not integers. So these are all defined, provided that t is not equal to 1. So one have a nice one parameter family of 2D TQFTs. So, and these 2D TQFTs are just usual 2D TQFTs, not in any generalized sense.
Okay, thanks.
So following up on that, is there then an interpretation of those coefficients? I mean, so then instead of having, so in those Verlinde coefficients, they are valued in this ring of rational function in T, right?
Yeah.
So is there a Hilbert space interpretation, at least in 3D, of that?
Yes. So in 3D, one just look at a particular infinite dimensional Hilbert space, and then there's going to be an action of U1, and then one use that to resum it. For example, if I have just a U1 action on C, then I'm going to have 1 plus T plus T squared plus ... if I'm summing over all holomorphic functions, right? And that's sum to 1 over T. So the equivariant Verlinde formula, as associated with this, here associated with like punctured surface, or more generally, heterogeneous thing with punctures, it compute a particular Hilbert space of 3D theory with some insertions on the Riemann surface. And it can also be viewed geometrically as counting certain homomorphic section of some line bundles or some non-compact space, but that non-compact space has a nice property that there's a U1 action, and the fixed points are actually going to be compact. So here, the U1 action only fixes the origin. That's something compact, allowing you to regularize this sum.
Thanks.
So in this type of construction as well, the Hilbert space kind of depends on whether this infinite dimensional Hilbert space in 3 dimensions, it depends on whether the parameter t is kind of inside the unit circle or outside, presumably.
Yeah, that's right. So here, natural assumption is that one start with something, the t that is actually just close to a 0. And then, everything turn out to be some nice analytic function that can be analytically continued. But maybe it's also, I guess, a good idea to have the perspective that when it's outside, maybe one actually need to use a different formula. So one need to So that's actually maybe more natural from the 3D perspective.
Yeah.
So here I'm just describing the story that is extrapolated from a small disk around the origin.
Yeah. Okay, any more questions? All right, well, maybe we can stop the recording, and then if people want to stay and chat a bit more, then they're very welcome to do so.
Okay.